So I hope you had a good time in the last 2 weeks. I understand there is some issue with the exam, the time of the exam. Unfortunately, I mean, the original date, I don't know what it was not coordinated with me, and I'm not going to be in Israel during most of February. So I don't know who decided it, but it's a good idea to put the lecturer in the loop when you decide on exams. So anyway, it was moved to March 4. I'm going to be in Israel actually between 28th of February and March 5 or 6. That's it. And then I'm not again in Israel until May. So those of you who cannot make it during first week of March, will have to wait till I'm back again, which is early May, unless you have some other ideas. But that's it. I don't want to have an exam without me present. I mean, this is not a good idea. So I'm sorry about this confusion, but somehow someone here coordinated it without talking to me. It's not very. Anyway, that's it. Now we talked last time, if you remember, about the Cramer-Rao bound. So we talked about minimum variance, the estimator. So remember again, we talked. I'm going to finish today the discussion of the statistical estimation of parameter estimation. There are several issues that I want to discuss today. First of all, the Cramer-Rao and its generalization, I mean the multivariate Cramer-Rao, the notion of efficient estimators, and the exponential families. Then I'm going to talk about efficient statistics, which I guess you didn't discuss with Ravid yet. He didn't do exactly all I wanted, but actually we're not aware of the fact that you are not here this week. So he did only 3 lectures, as far as I know, not 4. So we still need to complete. Next week he is not here, but so I'm going to have now 3 consecutive lectures. I mean today, Monday, and next Wednesday, and actually next Monday as well. I mean 2 weeks from now. So we're going to cover a little bit of the close the holes. So I'm going to finish the issue of statistical estimation today and on Monday, and then start to talk about information measures, entropy, Newton information, and how it's related to statistical estimation, and all that. And then we'll have a big chapter, or 3 consecutive lectures on information theory. Okay, so that's just to coordinate you. And again, I'm more or less following the order of Amir's lectures. He has a few things that I don't talk about, which I highly recommend to read. And I have a few things that he's not talking about, so together we should cover everything. Anyway, so you remember that when you get a sample, there is some source, so there's some parameter, parametric family. We generate samples through the notion of parametric family. So this is some sort of so this is the parameter space. Parameters which can be high dimensional. This is which is essentially was our world state in some sense in the Bayesian decision problem. We generate samples. We usually assume that they're IID. So this can be n-dimensional samples. Take an IID from this distribution. If we are Bayesians, we actually assume that there's some prior on the parameters as well. But if we are not Bayesians, we usually don't want to assume that we know this prior, but that's what we do in most cases. Those samples, from these samples, which are essentially, so in this classical Bayesian picture, these are the observations. Okay, and from that we are trying to estimate the parameter. So we generate functions of the samples, which I denoted by theta hat, which is this is the general standard notation. It's a bit confusing. So this lives again in the same space as theta. So if this was an Rn or some subset of Rn, this is also in the same place, actually. And we want, so these are vectors, real dimensional vectors, or complex, never mind. So we can actually talk about them as random variables, and we can actually talk about least square distances and other things like this, which we can do on. But this, in our Bayesian picture, this corresponds to decisions or actions in a generalized sense. I mean, this is deciding on the state of the world. Okay, so this is summarizing everything we said so far, and of course, we concentrated on the probability of the estimate, which is a function of the random sample, so it's a random variable on its own. So the random sample is some IID, or usually we assume IID here, and this explicitly says something else. And so this is a random variable, this theta hat, and it's conditioned, of course, on the true theta, assuming that there is a true theta. So the data is actually taken from this parametric family. As I already said many times, this is not a realistic assumption on when we work on real-world applications, whether there are, vision, images, speech, or neurons, spikes, whatever. Assuming that we know the parametric distribution is a very strong assumption. We usually don't. But that's the story so far. So this distribution, we said a few things about it. So among other things, if we look at this axis of theta, this it's in general multidimensional, but I draw it as a one-dimensional line here. So if this is the true theta, for a given n, this distribution of the parameter of the probability of theta hat given theta, just denoted by theta n for simplicity, it has some distribution, and we know that if it's unbiased, then the average of this distribution is theta. The mean is theta. So for unbiased distribution, the expected theta hat is at the point the true theta. If it's biased, it may shift. If it's consistent, asymptotically it's converging to theta in the large n limit. This is what we call consistent. And we care about essentially the difference. So let's say this is the true theta and the mean is something else. I don't know, this is the true theta and the mean is this. So they may be different, and this is what we call the bias. The bias of theta hat. The difference between these two. Theta hat minus theta. So the bias of theta hat given theta was theta hat minus theta, and this is a function of the sample size, or not only sample size, it's a random variable which depends on sample. So this is the expectation of this on the samples. Okay? So if this expectation is 0, we say that this is unbiased. This is the bias. If this expectation is not 0, it's a biased estimate. Okay? The variance of this distribution, which is the width, so the variance of theta hat, it's a random variable, so this is defined just like any other variance. It's the expectation with respect to the samples condition on theta of theta hat minus the expectation of theta hat square. Okay? Again, this theta hat is a function of the sample. I just write it like this. Okay, so this is the usual variance. So the square root of the variance is what we call the standard deviation. So this width is the square root of the variance. Okay? Is this clear? Just to remind you what we're talking about. So my notation here is a bit sloppy, but never mind. No, so this is the variance and the bias, and we actually said already the MSE, the mean square error, which is simply the expectation over this condition on theta of theta hat n minus theta square, not minus the expectation of theta hat, but minus theta. This is the true spread, the true least square deviation is factorized this into the bias square, or it's plus the variance. And this is the variance given theta. Okay? And okay, so this is the decomposition, the bias variance decomposition. And if we are talking about unbiased estimators, the bias is 0, and the MSE is just the variance. Okay? Now, we showed, so this is again this bias variance composition. And we usually, this is what we want to really minimize. Now then we show that for unbiased estimators, if the bias is actually 0 for all n, yeah, okay, consistency was something else. I mean, the whole thing, the distribution eventually shrinks into a delta function on the true parameter. But for unbiased estimators, so if b theta hat given theta is 0 for all n, this is what we call unbiased estimators, the variance of theta hat n given theta was bounded below by 1 over n times the Fisher information. And this is the Kramer-Rao bound. So the variance cannot be too small. Okay? It's bounded by something, and this j theta, which is the Fisher information, that's definition, that's the name, is was what? So we gave one expression for it. It's the expectation over the samples of the score, or the log derivative with respect to theta square. And we actually showed that the expectation of the score, this was easy, the expectation of the score itself, what was it? 0. So this itself is also the variance of the score. The mean is 0. And we asked you to show, I believe that Ravid actually showed it, this is actually equal to minus the expectation of the second derivative. Again, everything is taken at a given theta. Yeah. So this is a function of theta. So you know how to show this? Okay. So this you know. So this is nice because this is what we sometimes call the Hessian matrix. And if we take it at the peak of the distribution, this Hessian matrix, and it's unbiased, so this is the second derivative at theta of the peak. It's actually the Hessian matrix of a parabola, of a Gaussian, is precisely the 1 over the variance of a Gaussian. So this is more or less where I ended my last lecture. So if you take a Gaussian, for a Gaussian distribution, for normal or Gaussian distribution, so this is log p of x given mu and sigma, the parameter here mu and sigma. This is theta now, it's two-dimensional. So mu and sigma of a Gaussian. The log p is simply minus log half log 2 pi sigma square, the way it is written. minus half 1 over 2 sigma square x minus mu square. Okay, so this is the log of a Gaussian, the ln of a Gaussian. Is this clear? Nothing mysterious here. So now we can actually calculate the Fisher information for this for the Gaussian. Notice that there are two parameters, mu and sigma. So we somehow need to generalize this one-dimensional definition to a two-dimensional definition, actually n-dimensional definition. I think that Ravid also did this. I just want to remind you. So for multivariate, so for normal distribution, this is the Fisher this is the log likelihood or the log probability distribution. And for multivariate theta, so let's say theta is a vector, theta 1 up to theta d-dimensional vector, finite dimensional. So there's a natural extension of the Fisher information, and this is a multidimensional extension. So what is it? So the Fisher information is now becoming a matrix, which is a function of all those parameters. And so if I just, the natural thing to do, there are two, this is a covariance matrix essentially. The variance goes to a covariance matrix. This is the natural extension of a variance to multi-dimension. The covariance matrix is going to be again the second moment matrix because the means are 0 in this case. So it's going to be, again, the conditional expectation of d log p x theta to d theta I times d log p x theta, this is multidimensional, to d theta j. Okay? So the expectation, and this is an ij, so both I and j goes from 1 to d. So this is a d-dimensional matrix, square matrix. It's symmetric and positive definite or semi-definite matrix. It's just like a covariance matrix. Okay? And of course, this should be equal, again, to minus the conditional expectation of the second derivative to d theta I d theta j. So again, if under some technical conditions that the derivatives are continuous and twice differentiable and all the first derivatives, so of course I need everything to be twice differentiable for that. If it's a continuous second derivative, then the order of the derivatives doesn't matter, and this is again a symmetric matrix, and it's exactly the same thing. Is a minus sign, and this is exactly what we call the Hessian matrix in general. And if it's calculated at the peak, at the maximum likelihood, then the first derivative is 0 because it's a maximum, and this characterizes the width. So if I calculate, so this is the multidimensional, or the matrix D on D Fisher information. Okay? Now, so this is clear, I guess you saw it. Let's just calculate it just to understand what's going on for the Gaussian. I think Ravid did this also, no? Did he show this here? So I'll just do it. So I want to take, to actually calculate it for the Gaussian. So this was the Gaussian. I need to take, so it's actually easier, in many cases it's easier to calculate the second derivative than to calculate this product. So it's good, practically it's much easier to take derivative. So let's take the first derivative with respect to mu. So the score itself, d log p x mu sigma with respect to mu. And then, so what is it? So the first term doesn't contain mu. The second term is simply a linear, a quadratic function. So the two cancel, it's 1 over sigma squared. So this is minus 1 over sigma squared x minus mu. Okay? The first derivative, it's the first derivative. I didn't say there's a minus. Okay? There's a minus here from the Gaussian. Okay? Yeah, x minus mu. Yeah, okay. Doesn't matter. Plus. Doesn't matter. I'm going to take second derivative and the minuses. Anyway, so the second respect to mu and sigma. So what is it? So we have to take the derivative of the log. So this the 2 pi disappears. That's log 2 pi is a constant. So it's 1 over sigma square times the derivative of sigma square, which is sigma. So what is it? So it's the derivative of the log is 1 over sigma square, and then the derivative of sigma square is 2 sigma, so it's 1 over sigma. And there's a minus sign. No? Yes. No, there's no minus. Yes, there is a minus sign. Never mind. Okay. And
It should be 2 pi.
2 pi, forget about the 2 pi, because I just take the log. This is the log of 2 pi plus the log of sigma square.
Yeah, I mean, you should put the 2 pi sigma square, 2 pi sigma square down there, right?
Also 1 over
Yeah, I think it's gone. I don't care about it, because this is simply half log 2 pi plus half log sigma square, or log sigma. So log sigma is 1 over sigma. Yeah, it's 1 over sigma. There's actually a minus sign. But this is only the first part. What about the other part? So it's again the derivative of 1 over sigma square is what? Well, in phi was a long time ago. Okay, so 1 over x squared, what is the derivative? Anyway, so okay, calculate the derivative of 1 over sigma squared. So it's x minus mu. Yes, x to the minus 2. The derivative is minus 2. X to the minus 2 plus 1. So x to the minus. Derivative. Yeah. Okay. But I have 2 sigma square. Yeah, that's all right. A bit ugly, but never mind. So so this is minus 1 over sigma square sigma to the cube x minus mu to the square plus. Okay, never mind that. Now I take another derivative. Forget about. So anyway, so the second derivative is actually easier. So you get sigma square here. Let's take respect to mu first. For the second derivative of log p x mu sigma to d mu square, what it is? So it's this derivative with respect to mu. So it's 1 over sigma square. There was a plus minus 1 over sigma square. And the second derivative here, the mixed derivative, I take this with respect to sigma, I get sigma cube again, and so on. Anyway, so it's just taking too long, but you see what happens. So there are some functions of mu and sigma, actually 1 over sigma cube and 1 over sigma square, and mu eventually disappears from the second derivative. Doesn't appear there. So the score j of theta in this case is actually some function of sigma, or 1 over sigma, as it should be. Some function. All the terms depend only on 1 over sigma. Okay? You see why mu disappears?
Yes.
Because I take another derivative. It doesn't disappear from here.
It's written the expectation, I think.
Yeah, and then take the expectation will disappear. That's right. So eventually it should be a function of sigma. That's the only thing you should remember. And eventually the second derivative is just the Hessian matrix of the maximum likelihood in this case. Okay. So I didn't just to show you how it's done, but it takes too long. Essentially, this is what you do. You calculate this mean of second derivative. Theta I, theta j. In this case, it's the mu. Theta 1 is mu, and theta j is sigma. So you take all the mixed derivatives. Okay. Now, at the maximum likelihood, as I already showed you, of a Gaussian, since the first derivative disappear, the second derivative is exactly the second derivative of this with respect to mu, with respect to x actually, the maximum likelihood is exactly 1 over sigma squared. So I think I showed it to you already. So when we looked at the probability, the density of theta hat, so this was the probability of theta hat. So theta hat is actually x, and theta is a parameter for this distribution. The variance of the estimator was exactly the variance of x here, which is 1 over sigma squared. So the second derivative and the Hessian matrix and the variance are exactly the same. Okay, so this is just the Hessian matrix.
What is the x here? Why is it very
Now, so remember, this was a general Gaussian distribution. X was the variable here, and mu and sigma. But now when we look at our distribution of the estimator, this is actually our x, because I'm talking about the distribution of the estimator. So the distribution of the estimator was normal, and the mean of this normal distribution is simply the second derivative with respect to x at the maximum, which is just 1 over sigma squared. So indeed, the fact that the efficient information is the Hessian matrix completely coincides with the fact that it's the covariance matrix of the estimator at the maximum likelihood.
Why is it normal? Just assume?
No, it's normal because of the central limit theorem. So we saw that the score is an additive, a sum over the samples of many, many variables. The scores are independent, and because central limit theorem is divided, multiplied by square root of n, it's converging to a normal distribution. So central limit theorem tells us asymptotically it's going to be normal, and this fact that the efficient information is precisely the Hessian matrix coincides with the fact that the Hessian matrix of a normal distribution is simply the covariance matrix.
So it happens only in the limit.
So in the limit, that was essentially the proof that theta ml in the limit is both consistent and efficient. So in the limit, the parameters go to what they should go, this consistency, and the variance goes to the Fisher score. So in the limit, it's both consistent and efficient. And just remind you, efficient is something which obeys the equality. So it's actually a minimum variance. So efficient estimate is the same as minimum variance. Okay, so this was just essentially a reminder, and I guess you actually get some exercises to calculate the Fisher score for, let's say, Poissons and maybe other distributions. I don't remember exactly what was this was the idea. Okay, so the fact that it's actually the mean minus the second derivative is very convenient, because this is precisely what brings us to the covariance matrix at the peak, which is again the second derivative of the peak. Because for a Gaussian distribution, the second derivative with respect to x at the peak is exactly 1 over sigma squared. Okay? So if you take it with respect to x, take this and take the derivative with respect to x, twice you get 1 over sigma squared. Okay. So there's one thing I still want to complete. So what happened? When is there an equality or what are the distributions for which there are efficient estimators. So essentially, if you remember, this was based on what inequality? On the Cauchy-Schwarz inequality. So just to remind you, so again, those of you may not remember what Cauchy-Schwarz was. So Cauchy-Schwarz was essentially, as I said, it's easier to remember if you think about cosines of angles. So the Cauchy-Schwarz was based on the fact that the expectation of two variables, x times y, let's say that they're both 0 mean, it doesn't really matter. Square is less than the square root of the variance of x times the variance of y. No, the square of it is less than this was the Cauchy-Schwarz inequality. This is that's some value here. Of course, the negative is of course if it's negative, it's of course more. So this is Cauchy-Schwarz. It's actually a version of Cauchy-Schwarz. Cauchy-Schwarz in general for two vectors tells you that the scalar product, the absolute value of the scalar product is less than the magnitude of the mean of the norms, which is again essentially that the cosine of the angle is less than 1. That's or equal to 1. So this so when there is an equality here? So there's an equality in Cauchy-Schwarz in general when these two vectors are parallel or anti-parallel, where the angle between them is either 0 or pi, because then the cosine is 1, okay, or 1 or minus 1. So for equality, there's equality here if x is proportional to y. In general, there is still an equality here even if I shift it. So there is, let's say, another constant. So in general, when x is a linear function of y, or y is a linear function of x, then we have equality in Cauchy-Schwarz. Because this is actually the expectation minus the mean, so the constant will not change anything. Okay, so if there is a linear relationship between the two random variables, then we have equality. Okay, so when there is an equality here, what are those estimators which actually are efficient, for all n? So we want essentially, so if we apply this is a condition equality. If and only if this is true. Okay, so let's translate it to our problem. What does it mean? So here we have the variance of the estimator, which is a function of the sample, times what? The variance of the Fisher score, times j. Okay? So in other words, this can happen only if d log p x theta to d theta is a linear function of my estimate. So which means that there exist two constants. Let's call them a prime, which may be a function of x. So this is a variable with respect to x now. No, this was averaging over the x's. So this can be a general function of so it can be what I call here lambda. So let's call it lambda. So lambda can be a function of theta times the estimator, which is a function of x, plus constant, but this constant can be a function of theta, so some plus other function of theta. Okay, so this linearity. Remember that you're talking about two variables. So this linearity is with respect to the variable on which I average. So this is what we get. Conditions if and only if this happens. So this is the sufficient. That's the condition for equality. Just want to emphasize again, these constants here can be functions of theta because there shouldn't be a function of x, but there can be a function of the other variable. So now I integrate. This is just some sort of differential relationship. The derivative is a linear function like this. Now I integrate, but the integration is with respect to theta. So I integrate this. Let's write theta prime here to confuse you. And I integrate everything up to theta. Okay? D theta prime. Okay, so integration gives you that log px theta is the integral of this lambda. Let's call it, this was lambda 1, let's call this lambda, function of theta, times this function of x, the same function of x, plus the integral of this, let's call this, if this was eta prime, this would be eta. Okay? But now I did an integration, so there can be another constant. Let's call it c of x. This is an integration, and it's a non-specific integration, what we call integral לא מסוים.
No, it's not even only.
Why not? I mean, I just took this and integrated it, so it's equivalent. I did a very general integration, so I added a possible function of x.
No, but if the integral is equal,
Yeah.
it doesn't apply the original function equal.
No, it's the integral לא מסוים. It's
For every theta.
it's a if you have two functions which are equal, then the integrals are equal. האינטגרל הלא מסוים שלי also equal up to a constant. Up to a constant, they must be equal. Okay. So when f is the integral, f is the integral of little f, and g is the integral of little g. This is always infial. Of course, if there is derivative, this follows. But if I add up to a constant, this is always true. Okay, so I added a constant. It's a primitive function of an integration. I just solve the differential equation. So, this is the constant that I must add. Yeah.
Why is the integral?
If you have two functions that are equal, their integrals.
No, but why are the integrals?
So I'm saying that's what I just said. I mean, you have equality between two functions.
So why are the
If you integrate both sides, you get up to the difference can be up to only a constant.
okay? Then why is the function equal?
And the functions are equal because this is the condition for equality. So this is equal to this, okay? Without the integration. I just made it too complicated. Forget the integration, okay? This is the differential equation. I don't know how to. Maybe this is easier. This is the differential equation for p. I know that the derivative of p is a linear function of this form. I integrate it in order to find the primitive function. Now, when you integrate, there are constants of integrations that can come up. Okay? This condition is this one.
But we're talking about the variance of theta s and j. So
Yeah, so a condition for equality in Cauchy-Schwarz is that x is proportional to y.
yeah, but these are not the x and y that you were talking about.
These are the x and y I'm talking about. So the y was the Fisher score.
So what is the Fisher score?
J theta was the variance of d log p to d theta. So y is actually d log p to d theta, and x is my variable, the random variable type sampling. So this is y, and this is x. And I wrote it differently. Okay. Okay. So this is my y. Y is the derivative. So the derivative must be proportional to this. This is what it means. Now I simply integrated and I got this. Up to this constant, which may be a function of x because the integration was with respect to theta. So it's a bit confusing. Here the expectation was with respect to x, so they had to be proportional, and then theta is the constant. But then I integrate with respect to theta. So now this type of distribution where the log can be written as a product of a function of theta times a function of x, plus maybe a function of theta plus another function of x. This type of distributions are precisely what we call exponential forms. And I'm almost out of time. So this is just a definition. Exponential forms are functions. So now forget about this was an estimator. This is some function of x. So in general, it can be a complicated function of x. Actually, we assume that it's unbiased, but it doesn't really matter. If this happens, if you take the log of the distribution for x and theta, so there's a parameter and variable, and the log looks like a product of functions of the parameters sometimes functions of x plus some additive function which are only of the parameter or only x. This is our general definition of exponential form. So let me remind you, I mean, we already saw these families. For example, a Gaussian. So look at the Gaussian. So it doesn't look exactly like this, but if I open the parentheses, this is the function of the parameter only, sigma. And this is the function of x and mu, but you can break it. I open so it's 1 over 2 sigma square, x square minus 2x mu plus mu square, okay? This is a function of the parameter times a function of x, the second moment, plus a function of the parameter times a function of x. This is x squared, this is x, plus another function of the parameters only. So a Gaussian distribution is of this form, okay? And so the Gaussian family, the univariate or the multivariate, doesn't matter. They're all exponential forms. Bernoulli, I already showed it to you. Maybe you don't remember. So Bernoulli variables and are also exponential forms. Think about it. Let's just take another example before the break. For example, a Poisson distribution. So is this exponential family? What do you think? So a Poisson distribution, p lambda of m is e to the minus lambda over m factorial, or e to the minus, this is the right way, e to the minus lambda, lambda to the m over m factorial, or whatever. This is Poisson. Okay, the variable x here is m. It's a discrete, the number of occurrences, the number of spikes, whatever. Is this exponential? Yes, of course. Let's see. Log of p, so this is actually p of m given lambda. Lambda is the parameter here, the rate. So m given lambda is what? It's minus lambda, this is ln, yeah? Plus m ln lambda minus ln m factorial. Ln, yeah, just to make sure. Okay, so this is a function of x. This is a function of theta. How did I write it? Eta of theta. And this is a function that depends on the product. So this is just x times, so this is my theta hat of x, some function of x. So in general, a general exponential form, multidimensional, can be written in this form, some sum of function of the parameters, I call them lambda, let's stay with lambda, function of the parameters times some other functions of the variable, plus maybe a function of the parameter. I think in the lecture notes I should write these as b's, never mind. So this is c of x plus d of theta. So anything which looks like this is an exponential form. Okay? In this case, the function was actually the estimator, but it doesn't have to be. I can always shift it. Okay, remember this. We are going to take a break. I want to now dive into the properties of those families and show you some very important properties of them. So these are all the nice families that you all remember. I mean, Bernoulli, Poisson, Gauss, chi-square, gamma, whatever. I mean, all those classical nice distributions that in statistics they like to teach us, they're all of exponential form one way or another. Sometimes it's not so easy to see. You have to play a little bit with the log. But not only that, we know that the estimator, an efficient estimator, is going to be made out of those functions, which are a function of x that multiply the function of the parameter. So I'm going to explore this further through the notion of sufficient statistics. This is actually very important because it's going to take us further into much more interesting things and actually introduce the notion of information in a very nice way. So the next hour is very important. Don't go away. אמרתי, זה יכול להיות כאן היה אחד ממדים. אבל אם היה לי כאן רק כמה ממדים יכולים להופיע בכמה אינטגרלים. אז נעשה אינטגרציה ביחס לכל אחד מהמשתנים האלה, אז כל אחד מהם יכולים להתקיים כזה. ושם... ולכן כתבתי בסביבה.
פונקציות לא וקטוריות, הפונקציות האלה הן שקלה.
לא, זה אומר, תטא פה יכול להיות וקטורי.
אבל פונקציות A, B ו...
לא, הפונקציה קטנה. זה יכול להיות וקטורי, זה X יכול להיות כמובן וקטורי, אנחנו לא צריכים טוב.
לא שמתי לבדל, A ו-B לא יכולים להיות וקטוריות.
לא, A ו-B הם פונקציות סקלריות, הממד פה זה ממד הפרמטרים. אז תכף נראה. אני אצלכם פה על הפרמטרים. אני אומר, יש במקרה כזה יש הרבה סטטיסטים. ראינו שבמקרה הגאוסי למשל. כאן היה פונקציה אחת כזה. את כל השאר היה רק במקומות שיש תערובת גורם שמכיל פונקציה של המשתנה כפול פונקציה של פרמטר. זה הדברים שיש לי פה. אלה דברים באמת חשובים.
אבל על מה אתה חושב?
אז אני הסתכלתי, באופן כללי יכול להיות D כאלה.
זה הפרמטר?
בגלל שיש D פרמטר. איך אנחנו נראה את זה? איפה? הנה, אז אני ראיתי את זה. איפה ראיתי את זה? חמחתי את זה כאן ראיתי. גאוסיאן נראה ככה, נכון? הלוג שלו זה פונקציה כזאת. אל תתני לעמוד מהכלים, את לא מבינה מה טוב שצריך. אז אני אומר, תעצרי אותי עם דברים כאלה לא רואים. זה, לקחתי את הלוג של גאוסיאן, זה לגמרי ברור. זה הנורמליזציה. עם גאוסיאן לקחתי את שורש שני פאי סיגמה E במינוס X מינוס ניו בריבוע כשני סיגמה בריבוע. לקחתי לוג, קיבלתי את זה. לקחתי לן. אני חושב לוג זה לא מעט. או לוג, או לן או לוג 2. עכשיו, הדבר הזה זה פונקציה של הפרמטר בלבד. סיגמה. זה מכיל מכפלות. זה פונקציה של סיגמה ו-X בריבוע, סיגמה בריבוע X בריבוע. יש כאן עוד, אז יש כאן ככה. בואו נכתוב את זה פה יותר מסודרת.
אבל אין פה את הכובע הכפול.
כן, יש תטא כובע, זה לא תטא כובע. זה אמרתי, זה איזושהי פונקציה, קראתי לה אחר כך A שלי. בסדר? זה ה-A הזה.
אבל זה אמור להיות.
זה נכון שבמקרה הזה זה היה אסטימטור. אבל מה שיותר חשוב להמציא את זה פונקציה של A, של X. זה לא משנה, זה איזושהי פונקציה של X. בסדר?
אז יש פונקציה שזה אסטימטור.
לא. זאת אומרת, אני אומר, ההגדרה הכללית שלנו, קוראים לי שבמקרה של אסטימטור זה מי שמתקיים. במקרה של אסטימטור צודקת, הדבר הזה הוא גם לפי של unbiased אסטימטור. אבל זה לא חשוב. אני אומר, באופן כללי אני מגדיר Exponential Families בצורה כזאת.
אבל פה יש את אסטימטור וזה לא זה. זה לא.
אוקיי, צודק. אבל אני יכול לכתוב. אני יכול לעשות על ידי משחקים של העניין של אסטימטור, זה פחות חשוב מהעניין של פקטור. בואו נסתכל על זה עוד פעם. אז מה כתוב פה? אז כאן כתוב חצי לן של שני פאי סיגמה בריבוע פלוס או מינוס X בריבוע חלקי שני סיגמה בריבוע מינוס פלוס X ניו חלקי שני סיגמה בריבוע חלקי שניים חלקי פלוס מינוס ניו בריבוע חלקי שני סיגמה בריבוע. וזה כל הלן. וזה הלן של פי X של גאוסיאן. נכון? אז נגיד מה יש פה? יש כאן משהו שתלוי רק בפרמטר, עוד משהו שתלוי רק בפרמטר, משהו, בעוד שני פונקציות אין כמה שווה רק ב-x, לא חייב להיות, זאת אומרת, לפי x זהו 0, זה לא משנה. ויש עוד שתי פונקציות שהן מהצורה של פונקציה של הפרמטר כפול פונקציה של x, ועוד פונקציה של הפרמטרים כפול פונקציה של x. אם הייתי מפרסם את זה בצורה שכתוב שם, וזה אני רוצה לקרוא d of theta, וזה אני רוצה לקרוא, a1 יהיה פה x, ואתה 1, אז a1 זה x בריבוע, a2 של x ו-x, eta 1 זה פשוט 1 רגע שני סיגמה בריבוע, וכאן זה מיוק מקיישן בריבוע, וזה שווה לחצי לן שני פי סיגמה בריבוע, פחות מיו בריבוע. אז כל זה d. זאת אומרת זה משהו מהצורה הזאת. פונקציה של הפרמטר כפול פונקציה של x. לא, זה הכנסתי לכאן. זה, העברנו זה. פונקציה של x כפול פונקציה של הפרמטר. וכזה גם כפונקציה של x, זה x ל-x בריבוע. במקרה הזה a1 שווה ל-x בריבוע, במקרה זה a2, זה a1 שווה ל-x, ו-a2 שווה ל-x בריבוע. אז שני המומנטים, x ו-x בריבוע, התוכלות שלהם ממנים בשל את ה-SNN. אז זה בעצם נכון, זה לא בדיוק האסימטר כמו שהיה כתוב פה, זה לא שמדבר אותה, אבל זה לא חשוב, אני כרגע מסתכל על זה כאיזושהי פונקציה של x. עכשיו מה לא ברור? עדיין נראיתי במצוקה.
This d is the dimension of the...
Yeah, so this little d essentially the dimension of the parameters. That's what I'm doing.
Quick question, with Ravine we looked at using this for hidden variables, so you just add for x, you add a z. So a is...
No, if there is the story is a little more complicated.
That's what I want to ask, right?
Yeah, but then there are variables that are not this one. Okay, there are hidden variables. If there are hidden variables, then you need to average over them, sum over them.
Right, but in the form is still generally the same.
Yeah,
So
yeah.
you can add as many hidden variables without...
No, if you have hidden variables, let's say in a case like this, and you don't see the observation, hidden variables means that the probability is over x and some
Right.
h, something that you don't see, some hidden variables. And then the problem is that the probability of x alone is marginal. I mean, you have to sum of all the h's.
Right.
And then you get a mixture, so you get actually a sum of exponential forms. The sum of exponential forms is not an exponential. That's the real problem. That's why you need the n. Yeah, okay.
two-dimensional form. So it's kind of perfect with any line type of stream. And I also feel it's not necessary just because of that thing of only method for computation. But what? Yeah, yeah, but I need to research about it. Yeah, all the restriction about it is too long. I have to find all that how to get the most representative about that
Okay, so I just want to reiterate this. We saw that we said that in general anything that looks like this, where I can break the log distribution into a sum of products of function of the parameters, any function of the parameter, times any function of the variable, plus some possibly function of the variable only, and possibly function of the parameters only. Anything that can be written in this way is called an exponential form. Okay. Now, in the multi-dimensional case, where theta is d-dimensional, there can be d or even more functions here. But usually, the dimensionality, the number of those functions are not the rank of the functionally unrelated, independent. The dimensionality of the, I'm going to call them statistics. I mean, those parameters of the function of the variables is the same as the dimensionality of the parameter. Otherwise, you can reduce it to simpler form. So this sum is over the dimension of the parameter. D is simply the dimensions of theta.
So the sum is also on D, right?
Sorry?
Function D is also a vector.
D.
Yeah.
Yeah. So theta is a vector. This can be a sum of functions.
Different.
It doesn't have to be. I mean, this doesn't matter. I mean, the only thing that's really important in the exponential form is this: that there is a condition. It's factorized in the as function of the parameters times the function of the variable. And we saw in the Gaussian case that this is a factorization. So I get essentially, I mean, I open square, I get this. So this is a function of the parameter only. This is a function of the parameters only. And I have two functions that one depends on x squared of the parameters, the other depends on x in the parameters. So the statistics here are the two moments, x and x squared. And these functions that are called b are 1 over sigma square and mu over sigma square. Now I can play with this. I mean, when there are many functions, you can, in some sense, rotate this space anywhere you want, and without changing the distribution. This is essentially like diagonalizing the Fisher matrix. So since the Fisher matrix is positive, is a semi-positive definite at least. Actually, should be positive definite if its parameters are independent. And then it's a covariance matrix. It's a positive definite symmetric matrix, which means that I can diagonalize it, and so I can move to coordinate, or the parameters diagonalize the Fisher information. This is what is sometimes called the natural parameters of the form. And actually, and then in this case, this is just a very simple sum, and these are going to be the natural parameters. So I can always rotate. In this case, you saw the two moments, x and x squared, but you can also think about them as the mean and the variance. They're just functions, linear functions of each other. So they're dependent. It doesn't really matter.
So
yeah.
x and x squared are functions a1 and a2.
That's right.
And if they are unbiased, then they are the estimator?
No. Okay, so that's a bit confusing. So I show this for unbiased estimator and equality in the Fisher information. So this is a very specific function of x. It's an unbiased estimator. But I'm saying that in general, any function of x, if I can write it in this form, it's also an exponential. Okay? So I just generalize this in this. This is a special case of an exponential. But the function a is actually an unbiased estimator. It doesn't have to be.
Do you have a way of knowing if a of x is the estimator?
If this is an unbiased, then it's an unbiased.
If a is unbiased, then it means that a.
If a is unbiased in the sense that if but in general, okay, so I'm going to show you that in general you can estimate any estimator, any maximum likelihood or map estimation or everything is going to be a function of this. And that's exactly where I'm going now. So in the Gaussian case, it's x squared and x in some combination. I can take any linear transformation of them will also give me an estimate.
Yeah. But if A1 and A2 are the hexamer loads, I don't know.
Okay, so what's confusing here is that I started this by the Kramer-Rao, and I saw that equality in the Kramer-Rao must be of this form, where this was actually an unbiased estimate. But I'm telling you that this is not so important. I'm actually expanding this definition. This form is much more general than the. So any function of x only, anything which looks like this is good. Is what I call exponential form. So for exponential form, this for unbiased for efficient estimators, this particular exponential form has to be with an unbiased estimate of the parameter. Okay? But I'm saying this is not so important, and we'll see in a minute why. Not in a minute, in this hour. Okay. There is only one more thing I want to say about Fisher information. Yes.
So x squared is an unbiased estimate.
No, I'm not saying. It's exactly what I'm not saying. These are not unbiased estimators, anything. These are just functions of x. In this case, there are the two moments. So the average of x is going to be the first moment, which is actually an unbiased estimator of mu. So in this case, it's right. But the average of x squared is not an unbiased estimator of s of sigma. But I can cook from the average of x squared and the average of x, I can cook an unbiased estimator of both mu and sigma. And that's the general case.
I think if efficient estimators are like the holy grail of the parameter estimation.
No, it's more than this.
Like
No, efficient estimators are not the holy grail. The holy grail is what we call sufficient statistics, and that's what I'm going to talk about. So wait for this hour, and then I hopefully things will be a little clearer. That's becoming important. So just the only thing I just wanted to say here, I mean, there's a whole branch of statistics which is related to the Fisher information as a metric. So this covariance positive definite matrix is some sort of a metric on a manifold. And those of you who know something about manifolds and the differential geometry, we can take it a long way from here. I mean, so this is some sort of a curved miniature, a Riemannian manifold, and we can talk about geodesics and all sorts of things like this. And this is the beginning of what we call differential geometry, information geometry. I'll come back to this in some form. It's a differential geometry applied to statistics. And those of you who know something about these things, and I don't know, learned it in physics or in mathematics, there's a whole more that we can say here, but I'm not going to go this way this time. Now, although I like it very much, but it's not what I can do here now. The only thing I want to say that if there is a bias, this is actually an exercise. I don't know if you got it as the homework yet. If there is a bias, so can I generalize the Kramer-Rao bounds to the case of bias? You got it. So if there is a bias, nothing changed in the proof except that I actually wrote that theta is the expectation, the conditional expectation of theta hat with respect to x, so xn. This is the condition of unbiased. Okay? If there is a bias, you say, okay, this is not this, there is actually a bias. Okay, so this is again some function of theta. Okay? And you're going to show in your exercise, if you actually got it, that the only thing that changes is that you get that the variance of biased estimator is greater than, so in the numerator is going to be again n times j, so this is theta n. But here is going to be 1 plus the derivative of the bias squared. The derivative is the derivative of theta. So if the bias is constant, it doesn't matter. Nothing is constant. A constant bias is unbiased. So only if the bias actually is changing with theta, it matters. Because then I have to know what it is. But notice that if that this can be positive and negative. So I can actually reduce the variance below the Cramer-Rao bound by adding variables. This is important. So let's say if I make this a negative, small negative number, so it's a bias, but the derivative is reducing this numerator. Let's say it's -1. It's -1, I get a 0 variance. So -1 is a very bad, is a very strong bias. But I can reduce the variance below the Cramer-Rao bound by adding a small bias. And this is important. And actually, in machine learning, we do it all the time. We usually prefer to reduce the variance. You may want to hear me. Reduce the variance when we. Sometimes the variance is much worse than the bias. For example, if you want to estimate the temperature tomorrow, you really don't care about the slope of bias. If then you're going to be 20 degrees, but the variance is 10 degrees, you should probably take a coat. But I'm going to, I'm giving you a bias estimator. The bias is maybe 1 or 2 degrees, but the variance is only 5 degrees, the standard deviation. Then it's a lot better estimate. So in many practical cases, in medicine, in essentially everything, we prefer smaller variance at the cost of small bias.
Give intuition, like on why increasing the bias will decrease the variance. I mean, except there
You
might
still
be
haven't seen. This is something you're going to show.
No,
And you see that I can reduce the bound by adding a small bias with negative derivative.
I guess that you can show it mathematically, but it's hard for me to imagine.
Oh, no, so sometimes pushing, that's a fact, okay, mathematical fact, maybe not intuitive, okay. No, intuition is something you develop, you're not born with. You get used to things. So after you see that this happens, you begin to think, okay, how is it possible? I mean, okay, so indeed I can sometimes like pay a lot by pushing in the variance, in this bias-variance trade-off. I may reduce the variance by adding a little bit here, and everything can be still small. So I'm actually reducing this by adding a small variance and reducing the variance. And in many cases, when you have to make decisions about parameters or about, in medicine, for example, it's very important. If somebody's telling me, according to this test, you have cancer, but there's a huge variance, okay? So will you go and do chemotherapy because of that? I mean, that's a little bit risky. So you prefer to be maybe biased. I mean, I may be wrong, but I want to give an interval of certainty. And when you want what you call confidence intervals on your parameters, these are the important things. I mean, I really want to know, okay, my parameter, maybe I have a bias estimator, but I know with certainty that it's within this range. And I want this range to be small. And it's more important than this range is small, the confidence interval is small, than that it's unnecessarily unbiased. I don't care about the bias, I care much more about the width. That's something which statisticians classically consider the bias as the important thing. They want to be unbiased but that's not true. In most realistic decisions, especially those done with large machine learning algorithms, you care much more about the bias than the bias. It's much more important.
So if I put the neuron into the example of the doctor,
yeah.
so you will have it take another exam.
I actually want to reduce. I mean, before I do something very risky, I want to reduce the confidence interval. I mean, I want to make sure that I'm really sick, or I really need this treatment, or I really do need to. And so in order to reduce this confidence interval, you need to you want to reduce the variance of the parameter.
By getting more data.
By getting, no, not necessarily more data, by using a different estimator. Using a different estimator which will add a little bias, but actually reduce the variance, because the variance is really important. In many cases, you want to know the confidence of your estimation, not the value of the estimator. If the value is very noisy, you want to reduce the noise. Even at the expense of a little bias. Yes. My last question. Let's start.
The visual information is not dependent on our estimator, dependent on the probability in which we are sampling.
Of course, it depends on the estimator. I mean, it's visual information is the it depends on the distribution only, but you calculate it as the value of your estimator, and the value
I mean, by definition, I don't care about the estimator. Just look at the probability and then average over my samples. So the
No, what I'm saying, this was an equality which was true for unbiased estimator. Only if this is zero. If you allow bias,
if I choose a different estimator, then I just change the bias, but I don't change the Fisher information.
no, Fisher change is a function of the probability only. But I change the variance of the estimate.
Yeah.
That's what I meant.
That's what I meant.
Yeah, okay.
Makes sense.
The Fisher function is the variance of the estimator, one of the Fisher function, only for unbiased estimator. Yes, please. Yeah, it's a derivative of the bias. Because the constant bias, I really don't care about. Constant bias is unbiased. I mean, it's becoming pronoun if it's depending somehow on theta, but you can have a small dependence on theta which is not just there. But if you remember the 1 over n, the empirical variance, not 1 over n minus 1, is biased. Well, it's a very small bias, it's order 1 over n. So I don't care about it. It's actually easier to calculate in many cases I'm using it. Yes?
If the bias is depends on theta, then can you already say that to be small for every theta?
So let's say that I can. I mean, if I'm not sure it's small. Let's say that I put it to be minus half, okay? Bound it by minus half.
But you said that if it's constant.
No, not constant. I bound it by minus half. If I can bound the derivative. Bound it means there's a uniform line. It's not larger than minus half. Okay, so my variance is not the worst variance is going to be the maximum derivative here, which will still be smaller than the Fisher's. Okay, the Fisher, the unbiased case. Okay, so I want to switch to a new subject, which is directly related to exponential families, as you're going to see. It's actually going to lead us quite a lot further. So far we talked about estimators, and you saw that estimators are functions of the data of the sample. So in general, functions of the data of the sample. Let's call them some function of the sample. Of course, remember that the sample is taken from a distribution, some parametric distribution. So IAD, unless I say otherwise again. So this is called a statistic. It's a funny name, but that's how it's called. So a statistic is a function of the observation, the sample. Okay. So in particular, what we call estimators are statistics. Okay. So any function of the data is statistic. So this is the definition. Funny definition. It's just a name. Okay. A statistic. Now, the question is, so we saw that in some cases, some function of the data, for example, the sample mean, or and the sample second moment, let's say. In the case of Gaussian, this is the mu hat, and this is the x square. First two moments, let's say, of the sample. These are two statistics, which actually in the Gaussian case are enough in some sense. I mean, I don't need to calculate anything else from the sample in order to estimate the parameters. These two moments are enough to calculate what I want. So we actually say that, so this is the definition of what we call sufficient statistics. This is actually a definition due to Fisher. It's a bit funny, so, but it turned out to be very important. So statistic can be one-dimensional or multi-dimensional, like here. I mean, it can have several functions of the parameter of the data. This is one function. This is another function. These two are independent functions. I mean, I can't calculate first one from the other. Okay. So a statistic is called sufficient for theta parameter theta. So again, which can be multidimensional. So a statistic f, let's say, is called sufficient for the parameter theta if the probability of the data given the statistics and the parameter is the same. Remember, the statistic is a function of the sample, and the parameter is equal to the probability of the data given the statistics only. Okay, so this looks a little bit strange. I mean, this definition. This is actually the frequencies definition. The Bayesian view of this will be is actually more intuitive. If what I know, if the probability of the parameter given the statistics and the data is the same as the probability of the parameter given the statistics only. So this is more intuitive in the sense that everything that I can say about the parameter is captured by this from this data is captured by the value of the statistic. So in some sense, if you know the statistic, there's no more information about the parameter. Given the statistic, the data itself will not add anything. So these two are equivalent, but this is if you are Bayesian. This is if you are frequencies, you don't want priors on the parameters. So this means that the likelihood or the probability of the sample given only the statistics is the same if you know the parameter and if you don't know it. It's a bit funny. But the parameter doesn't add anything in this case to the likelihood of the data. If you're Bayesian, you can use Bayes' rule. This is actually telling you that the parameter, what you know about the parameter, depends only on the values of the statistics. So this is the intuitive definition of sufficient statistics. Now remember, in our Markov chain, I mean, we have the parameter, or the parameters, I mean, vectors of parameters that generated the samples, from which we generated the statistics. Okay, so this was the estimator, but now I'm not talking necessarily about estimators, I'm talking about this statistic, S of X. Okay? So this is the Markov chain that always exists. So this is the Markov chain. Remember, Markov chain means that this probability, so of course the probability of the statistics given the data and the parameter is the same as the probability of statistics given the data only. This is always of this Markov chain. If I know the data, I can calculate the statistic. I don't need to know the parameter. So this is always. So this is always. It is sufficient statistics if this Markov chain is also true. For sufficient statistics, long words. For sufficient statistics, this is also true. Which means, this is what this means. That I can calculate the probability of the data given the statistics only. I don't need to know the number of parameters. This is exactly what's written here.
But I don't understand the first arrow. Does it have some meaning? That there is no function.
No, of course. In principle, you can generate from theta. I'm giving, okay, this is theta. Now I calculate only statistics.
How can you calculate it?
Okay, I'm giving you the numbers. I'm telling you, let's say I sampled the distribution and the empirical mean was 2. Just giving you
But
the
you did sample
how I got it just here. I'm just telling you that the empirical mean was 2. And now I'm telling you, okay, calculate, this is what this means. This equality, which was so intuitive before, is exactly that. That probability of data given the statistics is independent of parameter, which means I can calculate this only from.
Yeah, I understand the
No.
rightmost arrow, not the left.
No, you don't understand the operational meaning. I'm telling you, somebody measured an expectation of a sample.
I don't know the statistics. I It's the statistic.
No, you're given the statistic. I'm telling you this was the mean of the sample. I'm telling you, I'm giving you a number. I didn't give you the samples. I'm giving only this number. And I'm telling you, okay, calculate the probability of one sample in this case. What is the probability that my sample included the value 1? So you just calculate this from the statistic. That's what it tells you. Probability of the data depend only on the statistics. I don't need to know the value.
Yes, but this is the rightmost arrow here. I'm asking about the leftmost arrow.
Yeah. How I generated this, I don't care. I mean, somebody measured the sample and calculated a statistic for me. Okay. What I'm giving you is only the value of the statistic.
Okay.
And I'm telling you the probability of the data of one of the samples of your depends only on this. This is what this equation means. So in some sense we are saying that S is sufficient statistics if both Markov chain holds. This one and this one. Okay? In general. Yes?
We understand that there is equivalence between theta and S, so the reverse.
It's not equivalent. I mean, theta.
Equivalence.
Well, in some sense, everything that I can say about this particular data depends on the statistics only. I don't need to know more. It's this particular data, by the way, this is important, just to confuse you a little more. It's not out of training data. So it's only what's called training, or the sample itself. I'm giving you a sample. And then I calculate the statistic. And now tell me what is the probability that one value in the sample was a certain number. So I can calculate this knowing the value of the sufficient statistic only. I don't need to know the value. That's essentially what it's saying. It's actually a practical problem. I mean, I'm giving you the mean of a population. And I'm asking you what is the probability that this mean you saw the value 1,000. Or you saw some outlier or something. And this you can compare only from statistics. It's a bit tricky because this is in training. It's inside the data, it's not outside it. You come back to this. So there's no generalization. Now, this is actually an interesting concept. I mean, because it tells us that in some sense that those statistics, I mean, those functions capture everything that I want to know about the parameter integral. So this is something which I find very. It's touching something important, which I want to call the relevant information. I mean, this is the only thing I really need to know from the samples in order to estimate the parameter. Everything else, this captures everything that the sample has. You can actually think about it this way as well. So instead of, if you give me this, I can predict the parameter just as good as if I could see the whole sample. So the errors here are a bit confusing, but that's actually the way to think of it.
It's more like the definition of the Bayesian.
Right. So this follows from this. So these two are trivially equivalent. So essentially this means that S captures all the relevant. This is actually my definition of relevant information. And I'll make sense of this later on. The relevant information in Xn about Xn. Okay. So that's the intuitive understanding. Yes. Okay.
And what you said about generalization, is it any different than the one saying the ability to generalize given X?
No, so this is actually a very delicate point. I'll come back to this later in the course, because we didn't really talk about generalization. But generalization means that I'm giving you data out of my training sample. I want to predict properties out of the sample. But then you can't really say that. It's not really clear. For example, if I give you more data, I can estimate better sufficient statistics, I mean, better values. So we'll come back to this. But yeah, in some sense, it's clear that for this particular data, this is sufficient statistics is giving me everything that I can say about the parameter. So this is actually much better, more interesting property, and we want to dwell on this a little bit. So so obviously the sample itself is a sufficient statistic. Trivial. A trivial sufficient statistic. So you want something better than the sample itself. Like two means, two moments, or something like that. So we define something called minimal sufficient statistic. And that's a really important thing. So a minimal sufficient statistic is the intuition is it's really the simplest possible sufficient statistic. But actually, so the way we define it, so a minimal sufficient statistic sufficient statistics, I'm sorry that I'm lazy. A minimal sufficient statistic, let's call it T of x of n, is a sufficient statistic which is a function of any other. This is again a somewhat funny definition. Any other sufficient statistic. Or in other words, if this is my parameter and this is my data and this is my sufficient statistic, I can always calculate from any other sufficient statistic something which I call T of x n. For any of these I can calculate this. So in some sense it's the minimum, and this is minimum. If I can calculate it from any sufficient statistic, I can reduce it to something which is still a sufficient statistic and cannot reduce it any further. This is going to be a minimal. So in some sense, these two chains should hold, but this should be on the left. It should be a function of any other sufficient statistic. I cannot reduce any further. It's the simplest possible.
But not for any data.
For any data. The simplest possible sufficient statistic. That's what it means.
For any given sample?
For any given sample, if you calculate this, you cannot reduce it any further. But let me give you another intuition. So the other intuition is that essentially any sufficient statistic is some sort of partition of the samples. So I mean, okay, so let's say example. Yeah. The most trivial example. S of xn, which is just the sum or the sample mean, is sufficient for mu in a normal mu sigma distribution. This is we know. We know we don't need to know anything more than this is actually show. Actually, it didn't show, but we know this already. Is this a minimal sufficient statistic? Yes, I cannot reduce it any further. But for example, I could calculate this in terms of two numbers. The average of the first half of the sample and then the average of the second half of the sample. This will give me two numbers, which are also sufficient statistics, of course, but it's not minimal. I can sum them and get a smaller simple statistic, and so on. So this is a sufficient statistic, and so it leads to a. So you want, and actually, in order to you can easily prove that for the Gaussian this is the case. I mean, you just directly see that if you actually know the sample mean, there's nothing more in the sample that can help you estimate the problem. So actually, we need a better characterization. I mean, slightly more easier to actually estimate. And so luckily there is a very important theorem, which I'm not going to prove, but if you want, you can find it in the book. It's a bit boring, but it's a direct route. So essentially what I'm saying is that a sufficient statistic, or any statistic, is some sort of partition. So I can take the space of all the samples. So let's just denote it. So the space of all possible samples is the huge space, beside n. We already saw this space when we integrated over all samples. So this is the huge, all possible, it's an n-dimensional, let's say x is a real number, so this is an n-dimensional Rn of all possible samples. Now I'm telling you where are the samples that have exactly the mean mu. So this is some sort of circle here or something, I don't know. All those is a subset of all the samples that have exactly mu. I tell you where all the samples have exactly first moment u and second moment sigma square is another partition. So any statistic is actually a partition of my samples into equivalent classes like this that have the same, it's a disjoint partition. So this can be mu1, another one here can be mu2, and so on. So I can decompose the samples into different values of the statistic. That's the trick that we use all the time. So essentially, this is a reduction from these n-dimensional numbers to one-dimensional numbers that essentially partition my space of samples into according to the values of the statistic. This is why, and when we say the simplest one, in some sense it's the simplest, it's the coarser possible partition of X, which is still sufficient. So a minimal sufficient statistic is the coarser possible partition, which is still sufficient for the parameter.
What do you mean by coarser?
Coarser, I mean that I cannot just make it any coarser. So that's why it's a function of any other statistic. A function of any other statistic means that I can join together the value of the other statistics and get something which is coarser. And the topology, which is how they say it. So there's fine partition is very, very delicate. Every point is, and then I start to merge these cells. And so essentially, we take a very fine partition. Okay, this is some sort of partition of my set, and then I say I group all this together, and then group all this together. And so the coarser one is the one which really has the least number of parts. You're right. I mean, I need a much better definition, and I will give you the better definition. We go into the value of the inertial transformation and entropy, but I still need to do it. Okay, so there is a theorem.
Each partition is a statistic or a minimal. I mean, each partition is a sufficient statistic or
No,
a minimal.
each partition is statistic.
Okay.
The minimal one is not necessarily sufficient. I mean, I can take partition which are just some partition of the data. A sufficient statistic, a sufficient partition, or sufficient statistic is a partition which is it's enough to tell you in which cell of this partition my sample is in order to estimate the parameter. Okay, so this is sufficient partition. A minimal sufficient statistic or minimal sufficient partition, by the way, we could use this term, a minimal sufficient partition, is the coarser one out of all the possibilities. I take all the possible sufficient statistics and I unify them in some sense until I get the coarser one. This is the minimal statistic. I know that at this point it looks strange, the whole thing, but it will take time to get used to it. So there is a theorem which really characterizes sufficient statistic very nicely, which is called the Neyman-Fisher factorization. Factorization theorem, and essentially it's saying the following: S of X is sufficient statistic for theta if and only if there exist functions. Now you see immediately this is not a very functions g of xn of the samples. No, sorry. G of xn and theta and age of xn such that this product is the likelihood of the data. Okay. So in other words, this tells you that if you can write the likelihood of the data as a product, I'm sorry. Yes, you should write as f of xn. Yes. Product of two functions. One function is a function of the statistical parameter, and the other function is a function of the data only. If you can write your data as a product like this, then S is sufficient. This looks very nice if it's true. So actually, it's easy to prove it. It's not that easy. As I said, it's technical to prove it, but take it as an exercise if you want. I don't want to prove it now. I simply don't have the time. But I want to use it. So let's look. So essentially, what it tells you that the log likelihood is a sum of some function of the statistic and parameter only, plus log of other function, which is a function of the data only. So you see immediately, for example, that the maximum likelihood estimator is a function of the sufficient statistic only. Why? So if this is true, then the log of px and the log likelihood is the log of age plus the log of p of s, xn, and theta. Okay, sorry, no, g of s and theta. Okay, we took the log, and then the log likelihood is the argmax of the derivative of the likelihood with respect to theta, and this is of course the argmax of the log g d theta. So it's independent of anything else but s, because this does depend on theta. So you see that, for example, this is the theta maximum likelihood. The maximum likelihood estimate, the argmax of theta, is the argmax of this. It's the solution of the equation this equals to 0. And so theta maximum likelihood depends only on the derivative of the log. So it's only, yeah. So the argmax, this equals to this, and therefore the argmax, this means the theta maximum likelihood is a function of f. Excellent. So if I have a sufficient statistic, the maximum likelihood estimate depends only on it. Now, let's take another example before we arrive at the point of business. In the Gaussian case, let's see that the factorization lemma actually holds. It's actually called the factorization lemma, not the theorem, but never mind. So just look at Gaussians. So it's very easy to see what is the sufficient statistic. Take, so a Gaussian, let's say that I have xi samples from a normal mu sigma. So the likelihood of a sample will be